Okay, so a very warm welcome, everyone, to our first meeting of the PROTEUS seminar series of this academic year. Today, our invited speaker is Professor Esfeld from the University of Lausanne. He's a leading philosopher of physics, and we are looking forward to hearing more about the ontology of physics that he's going to discuss today. Thank you very much, Professor Esfeld, for accepting our invitation.
Yeah, thank you very much, Sylvia. Now, I don't know you, or I don't know most of you, so I have prepared some slides, but these are philosophy slides about ontology. So I would like to ask everybody to interrupt me simply, because we are not 100 people, but 12 people for the time being. So I don't think it's necessary that I talk for all the time and then you ask questions. So if you find something questionable in the sense that you feel somehow uncomfortable about what is going on there, please interrupt me immediately. And if you think what I'm saying is wrong and another view is right, etc., then we can postpone this for the discussion. But I don't want anybody to leave the meeting or to get tired or so, just because it may be too much analytic philosophy in there, or later on too much physics, etc. So please interrupt me immediately. Okay, this is fine. So ontology of physics, of course, is a very broad subject, and we could talk for years about this, and we only have one afternoon. So I want to run briefly through a few questions. So I think that the philosophy and physics, so what was called natural philosophy in the old days, should answer three questions. So the one question is, what is there out in the natural world? So what is matter, what is space and time, and how does matter behave? So what are the laws of nature? What are the laws according to which matter behaves? And of course, for philosophers, this includes the question whether the laws are also in the ontology, and how this relates to our experience of the world. So how does matter and space and time, being subject to certain laws, explain the observable phenomena? And the more specific question I would like to pursue is whether we can discern, fix a minimal set of entities that form a common ground that can accommodate our physical knowledge. So as philosophers, we of course see and admire the progress of physics, but we don't want to change our ontology all the time when there's a change in physics. So is there something that can be taken to continue all the time? And I think there is. So I will throw a proposal now out to you and then discuss it. So the proposal I would like to present to you and to argue for is based on the tradition of atomism, which goes back to Democritus, which is implemented in modern physics since Newton, which to my mind still holds in contemporary physics. So for instance, if you open Feynman Lectures, which is a very good book on physics, also Feynman says that the atomic hypothesis still is the foundation of physics. And then the question is, can we purge this hypothesis in such a way that its core comes out, that we don't have any of the baggage in there, which is contingent, which we don't need at the end of the day. So atomism is about an arrangement of little things, call them matter points, and these matter points are such that they don't have any intrinsic nature. So it's about the way in which they are arranged, and they are spatially arranged. So we have relations of distance, they are apart from each other. So the first axiom, so to speak, is to say that there are distance relations that individuate simple objects, namely matter points, and then something goes on in the world. These matter points, they are permanent. the atoms don't come into being and go out of being, but the distances between them change. That is what's going on in the world. And the proposal now is that these two axioms are minimally sufficient for an ontology of the natural world that meets some further criteria, such as that it is coherent, that it is empirically adequate, etc. They are not necessary. They are sufficient, but not necessary. Of course, it could be otherwise. They are not a priori, so we are not engaged here in transcendental philosophy or anything such like that. And they are, of course, fallible. So physics can throw away atomism and teach us better things about the world. And what I want to do now in the next half an hour or so is to explain this proposal, advertise it by running first through philosophy and then briefly running through some major physical theories in a sort of a crash course. So one thing one could answer why parsimony should be a good criterion. So I put in there minimally sufficient, right? It should be sufficient, but it should not be more than what does this job. And of course, there is Occam's razor behind this, Occam's razor, which says that one should not multiply the entities to what one is committed beyond what is necessary for the purposes at hand. So there's a principle of parsimony, and I think this should go without saying, but perhaps it's nevertheless helpful to say a few words about it, in the sense that for any candidate entity, when someone says, when you're asked to say, what are your ontological commitments, you need an argument why one shouldn't endorse an ontological commitment to that entity. So the simple fact that you see it, or that it seems obvious to you, or that you have an intuition about it, etc., is not an argument why this is really there, because what you see, what your intuitions are, what figures as a variable in a physical theory, etc., that may well be there for other purposes, and you cannot directly read off your ontology from common sense, from your intuitions, from a mathematical formalism, etc. But if something is minimally sufficient for an ontology, and in our case this afternoon of the natural world, that contributes to there being a coherent theory that can explain the phenomena, I think that is the best argument for an ontological commitment. And if you think some people reject the principle of parsimony, and we'll see later on what they do and what they say, then they say, I mean, a richer ontology, the richer the ontology is, the more you can explain, or the deeper are your explanations, etc. But I don't think so. I think in ontology, a minimal diet is still required, and you run only into artificial problems and impasses, which can earn your PhD thesis, which can fill whole libraries, but nevertheless, they don't make any progress. Okay, so up to now, this may all seem innocent and going without saying, but it means that you cannot, in our case here, when we come to the ontology of physics, use the mathematical structure of a physical theory as the guide to your ontology, because the mathematical structure is there for a representational purpose. It seeks to give you a simple and informative representation about the world, and use a lot of means to do so, but this is not the ontology. Okay, so the ontology should really be the question then, which of this mathematical structure do you need to account for the world? And as I already mentioned, you need relations. Okay, and I worked for a long time on and continue to work on structural realism. And structural realism is the idea that relations have priority. Why do we need relations? Because we have more than one object in the world. That's the simple answer. So obviously there's a plurality of objects, otherwise you would not have change, and you would live in some philosopher's paradise of Parmenides or whoever it may be, but this would not relate to the real world. So even people who these days defend a priority monism, so Jonathan Schaffer does this and says the whole universe is prior, whatever that may mean, and however that may be, there still is a plurality of objects. So the universe, obviously, even if the whole universe, and if that should be a form of holism, is there, then there is an internal differentiation into a plurality of objects. And that in turn means that you need relations that carry out that differentiation. So there are some people out there in metaphysics, such as the late Jonathan Lowe, John Heil, to a certain extent also Anna Mamodoro, who think that the relations somehow who go back to Aristotle, so neo-Aristotelian metaphysics, and think that relations somehow are secondary and substances come first. But the problem is that you should know or you should tell us what makes it that these substances go together into a world, and then you need relations anyway. And if you have relations, you can employ them to individuate simple objects. So this is very anti-Aristotelian, what I say here, because the objects are simple, they don't have form, etc., that individuates them. And as you know from the long debates about Plato and Aristotle, it's very difficult to think of individuation through forms. If you have relations, they can individuate the objects. So if you have them anyway, let them do a job. And then you get to thin objects, so to speak. That's the term of Stephen French, thin objects, because there's nothing more to these objects than standing in the relations that individuates them. And that's what we had before. On that slides, we have distant relations, and they individuate simple objects, meta points, and these meta points, and these are meta points because they stand at distance relations. There's nothing intrinsic to them. So the relations are indispensable. They can give us a structural individuation of objects. And then we get as a benefit that we don't have to accept the numerical plurality of objects as a primitive, but derive them from the relations that individuate them. And when we go to physics, what's the best, what's the, so to speak, what's the natural candidate for the relations? That is distances. Think of Descartes. Descartes stands, Descartes' physics is not good, but his philosophy is much better. So Descartes says that the natural world is a res extensa. There are no Aristotelian forms in the natural world. There is just extension and motion. And I take this to mean that the things that we have in the world, they stand in distance relations. Now, a distance relation is irreflexive, so nothing is at a distance at itself. It's a metric, so if A is at a certain distance to B, then B is at that distance to A, and connex, which means that any objects in your set of objects are connected by a distance relation. In fact, the distance relation is the world-making relation, in the sense that all and only those objects for which it makes sense to answer how far apart are they from each other, are together in the same world, okay? And what we have here now, because we have parsimony as guide, is no particular metric. We only have ratios of distances in the sense that we can say A is farther away from B than from C, and specify this. So A may be the distance between A and C, may be the double of the distance between A and B, etc. So the distance relations give us the particles, so the number of particles or points or meta points that we have at the other way around. So if you have n points, then we have 1/2 n product n minus 1 distance relations. And this is now the substantial claim. We want the distance relations to individuate the objects, and this implies now that a certain price has to be paid to get the benefit that numerical plurality is not primitive, but that you get the objects out from the relations, and the price there is that entirely symmetrical worlds have to be excluded, because then the distance relations could not do the individuation. If the configuration were entirely symmetrical, all the objects stand in exactly all the same relations, and you could not discern them, you could not distinguish them. All this is just a more general formulation of Leibnizian relationalism. So Leibniz famously argued against Newton that space and time are a surplus structure. If space and time exist, they make differences. So there are different facts of which points of absolute space the given material objects occupy, without those differences showing up in any empirical one. And that's bad physics if you have distances that don't make a difference. It's bad philosophy in any case, and also bad science. So Leibniz says that there are only spatial relations, and he defines the spatial relations as those relations that make up for the coexistence of the objects that stand at that. Okay, so that's what I had in other words on the previous slides. This is just Leibnizian relationalism formulated in another way, namely that you individuate your objects by the relations, so that the distance relation, the spatial relation in this case, is the relation that makes it that these objects build a world and stand in a configuration. So here is a simple drawing of what we have there. So here we have 6 objects, and these 6 objects make up our world, and they all stand distances to each other, and it is such that you can individuate them by the distances. So take this as your reference point, your inertial system if you want, then you can say that one is more farther away from that one, and that even farther away, etc. You could take any of these points as your reference system and individuate all the other points with respect to that point. That is the idea. So, and for that idea to work, of course, the configuration cannot be entirely symmetrical, but then you get as result that why do you have 6 particles here? Because you have these distance relations that make up that you have 6 particles, and these 6 particles form a world because coexist because they are related by such relations. Okay, that's an illustration of the first basic point, but the word would be boring if that would be all. We have change. So now we have our meta points again, and their distances change. Okay, change is a primitive, also for Leibniz, and I think also for physics, because all the physics is there to find laws that capture the change that goes on in the world. So the history of the universe, you can imagine it as a stack of such configurations. So each such configuration can be a snapshot of the history of the universe, and there's change. And now consider the task that you get these snapshots and you have to order them. And the claim now is that if these, the snapshots of our universe, there is a unique order. Okay, first comes this configuration, then that one, then that one. Okay, and that order has a direction. So first this one, then that one, then that one. First the talk, then the discussion, then the coffee. Okay, not talk, coffee, discussion, but talk, discussion, coffee. So the order is unique. You cannot change that order. And it has a direction in the sense that we cannot go from coffee to discussion to talk, but we have to go from talk to discussion to coffee. Okay, so if this were the world, we have to go from the Big Bang, etc. To what happens then, and I don't know how the world will end, but perhaps in a thermodynamic equilibrium, which would not be fun, but it is hopefully still far away from us. Okay, so I hope you get the idea. We have spatial relations individuating the objects making up for a configuration. We have change. And we impose, I would say, Leibniz just stipulates that, and I think that stipulation is right. You cannot derive it from anything else, that the change is such that it is uniquely ordered and directed. But we don't have primitive time in here. Time, then that's why I made there a tau, but not the t. Time then comes from change as the measure of change. Leibniz says the order of succession as the way that enables us to write down laws for the change such that these laws bring out the order. But the time is the measure for the change. So if you imagine, but I mean, my capacities with slides are very limited, so I could have a second stack of these configurations. Let God have a problem. Leibniz thinks that God creates the best of all possible worlds. May not suppose that there are two worlds that are the best of possible worlds. So God creates two worlds. If you had an external time, you could ask what is happening now in that other world, or what happens 10 years after the creation in that other world. That presupposes an external time. If you have just relational time, you cannot ask that question across possible worlds, but you cannot ask it within a world because the change is unique and directed. So you can ask what is the order of time, and now you have some metric, and then you can ask how far away, how long did it take from the creation of the world to get to that configuration. Okay, so we have something in here which is more than some people in the philosophy of physics want for time. But then I say we need this. So if we throw away more, if we threw away, for instance, the directedness or the uniqueness of that order, we would get into trouble with having a theory that is empirically adequate, because in that case, we would lose the distinction between variation within the configuration. So there's variation because this point is closer to that one, etc. So it's not a symmetrical configuration, versus change in the configuration. So change is more than just variation. So that's why I have put in here, and some people think that this is too much, but I think I needed something which has a direction, and I think Leibniz, in fast that goes, was a great philosopher. Okay, and that's what that's more or less roughly what I wanted to say in 20 minutes about the pure philosophical side, and now look into how we get the physics in now. And this, of course, is too meager as a conceptual basis to do physics. So what we have here is, to use some chop talk, a primitive ontology. A primitive ontology is ontology because it says what is out there in the world, and it is primitive in the sense that you cannot derive it from anything else. Okay, at some stage, I mean, if you're neither Hegel nor God, Hegel thought that you could derive something out of nothing, or out of being and nothing. You could derive this, but usually philosophers cannot do this, but they have to accept something as primitive for the purposes at hand. So for the natural world, maybe a religious person thinks that they can derive all this from God. That may be so or may not be so. That's not my concern right now. But when you consider the natural world, you have to pose something as primitive, as what is simply there, what is finally the reference of our theories, what they talk about. That should be general, what you pose as primitive. It should be simple. And the idea of atomism is, and I think when you purge it of superfluous notions, that's where you get to indivisible objects that are not characterized, but characterized by their relative position, so that you get a spatial configuration of matter. That configuration changes. And now physics wants to account for that change. And if I give you just one snapshot, if I give you just the information about particles, the relative positions of particles, you won't be able to say anything about how this changes. So to get to a physical theory, you need more now. You need variables that give you something what a physicist would call a state of the world at a time here. Just the positions are not sufficient for a state, because you cannot do anything with them to find out how this particle will move with respect to that one, etc. That's why you introduce now something that I would like to call the dynamical structure of a theory. The dynamical structure is everything that comes in through the role that it performs in order to account for the change in the primitive object. Okay, so it has the function to determine the evolution of what is simply there. And you do this by introducing variables such as, for instance, masses. So if you give these guys masses and you define masses as gravitational mass, as that what makes things attract each other, then you will get at the end of the day a law that tells you if they are distributed in that way, so in the positions, if they have some initial velocity as how they change, and some masses, they will attract each other. And the law will tell you how they attract each other. And you need more, you need a geometry into which you embed the whole thing. So Newton was, of course, right in replying to Leibniz that for doing physics, you need a geometry with a space and the time in which you consider the whole configuration as embedded. Just with relations, you can't do physics. That was what Newton thought, and he is partially right about it, but partially wrong, as we know today. But in any case, you need more than the primitive ontology. And now the question is whether you should put that more into your ontology. Does this require further ontological commitments? And I would say no. And in order to give you a reason why one should say no before pursuing further the physics, let's bring in a further philosopher apart from Leibniz, namely David Hume, because David Hume had a great idea about laws, or at least that is what is today called Humean metaphysics. Hume had a lot of further ideas, and some of them may be great and others not so great. But when you speak today about Unionism or Humean metaphysics, one takes up the Humean idea that there are no necessary connections out there in the world, so no modality. Here in these entities, there's nothing modal in there, they are just there. So you don't need anything modal, and notably, you don't need anything modal to account for laws, because Hume says, David Hume, the historian, the Unionism says that everything that the laws, they come in for free. Once I give you the whole stack, the law, the whole development, the whole evolution of that configuration, the laws are nothing but the axioms or theorems of a system that allows us to represent that evolution in a simple and general way. So in a way that it is as simple as possible, as universal as possible, and as informative as possible. So that's the Humean idea. So the laws are nothing over and above in the ontology. They just supervene on, to use the philosophical term, or a better philosophical term, going back to Louis Jackson, these American-Australian guys who developed that metaphysics, is to say they are located in there. If you have all these matter points and all the evolution, you have the laws. The laws are nothing like governing them, steering them, or telling them what to do as civil laws are supposed to do if the people follow them. They are just a summary, a good summary of what these things do on their own. So they don't need a government here. They don't need governing laws. They just move in certain ways. Their movement is such that it's not completely chaotic, but exhibits certain patterns. And what expresses then these patterns, such as attractive motion, are the laws. Now, there's a position called superunionism in which I'm engaged, which goes beyond what the union metaphysics says, in the sense that it purges these of things that are not needed. So the background for union metaphysics is David Lewis, and Lewis had intrinsic properties at space-time points, so he gave something Aristotelian to the particles, namely intrinsic properties. That gets them into trouble because one cannot know these intrinsic properties. They are pure qualities, etc. So all the trouble that you have with Aristotelian forms comes then back. And Lewis thought you need properties so that it becomes not arbitrary, but relations can do that. So we have natural relations here. Distances are the only natural relations. And what superunionism then does is to apply the union strategy not only to the laws, but to everything which goes into the laws beyond the primitive notions. So the geometry, the dynamical parameters such as masses, charges, energy, etc., they are treated in the same way as laws, namely as coming in through the role that they play in the laws, insofar as they are means to achieve a representation of the overall change in the distance relations that strikes a good balance between being simple and being informative. And this now can be illustrated. So I shall stop in about 10 minutes, I guess. So let's run quickly through a few physical theories. So how could this work for classical mechanics? Classical mechanics think of Newtonian gravitation. You have certain patterns in the particle motion, such as attractive motion. And this implies, in order to capture this motion in the form of law, you need parameters that are defined through the functional role that they play for the motion of the particles, mass, charge, for instance, mass for attractive motion, charge for attractive and repulsive motion, and these can be attributed to the particles through their nomological roles. So Nat Hall had this developed, had this idea in a paper which goes back some 10 years or so, Barry Lower, etc. And if you think this through, you get to a view of classical mechanics in which the variables that are attributed to the particles are not properties of the particles. So you see now here the parsimony principle at work, the fact that the physical theory attributes variables to the particles and it gives them values that are constant, such as mass and charge, does not justify the inference that those are properties of the particles. Of course, the propositions are true. It's true to say that the electron has a certain charge and a certain mass, but there's nothing intrinsic in the particles that are electrons that makes these propositions true, but what makes them true is the way in which they move. So particle species are not intrinsic, but they are derived from particle motion. So some particles are electrons because they move electron-wise, so to speak. First comes their motion, and it is because their motion exhibits certain regularities that these particles have charge. So they really have charged and are charged, but not as an intrinsic matter, but as something that comes out of their motion. And if these very same particles moved in another way, they would not have charge. So you see here the union idea at work. So when Hume talks about causation, of course, there are causal relations out there in the world, but the causal relation is not intrinsic to two events that are related at cause and effect. Two events are related at cause and as cause and effect because there's an overall pattern in the world which makes them to be related in that way. And the proposition that throwing the stone at the window was the cause of the window breaking is true, but its truth maker is nothing intrinsic to the events of throwing the stone at the window breaking, but the general pattern of motion that manifests certain mechanical regularities. Okay, so the counterintuitive, what may sound as counterintuitive in the first place, is that and now we can argue what is the chart and the horse here, and what is counterintuitive here is to say the motion is the horse, and all the apparatus of the variables is what is driven by the horse. It's the chart. So the mass is the status as electrons, etc., and not the other way around. The electrons are not the horses that drive a car that is the motion. First comes the motion, then comes the attribution of such parameters, and this you can now do through the whole board. You can do it for mass, you can do it for charge, you can do it for energy, etc. All what you find, you can do it, of course, for the constants of nature, all what you find in your theory. So they are there. There's no anti-realism here. The Unionism is a fully fledged scientific realism, but a scientific realism based on a minimalist ontology. So some people get that wrong, and sometimes, and perhaps I didn't. Speaking, you usually introduce this in terms of representation, etc. But it's ontology. It's on Unionism. You can have a union theory according to which there are causes and effects out there in the world. It's just not an intrinsic affair. In the same way, of course, there are masses, charges, energy, etc. But it's not an intrinsic affair of objects, but it's an affair of how they move. You can treat in the same way space and time. So, of course, classical mechanics needs a geometry of an absolute space. It needs inertial frames, etc. It needs absolute accelerations, etc. But they come out of the change in the distance relations as being part of the system that gets us from the relations to a physical theory, and it is implemented in the relations and nothing beyond it. So that's so Hume enables the Leibnizian realist to say that they don't have to develop an alternative physical theory that is purged of absolute quantity. So not, but they can do so. So Julian Barber and his collaborators at Oxford since the 1970s do so with success. So they show that indeed you can have a physical theory that uses only relational quantities and no absolute quantities. That physical theory as a theory is, of course, more complicated than to do the calculations, etc. But nevertheless, it's an empirically adequate theory, but you would not see it taught in physics courses, because if the students have to learn how to do calculations, they use the easiest apparatus for the calculations and not the ontologically clearest and minimalist one. Okay, so let's use the remaining minutes for a quick look into quantum mechanics, say a quick and dirty look into quantum mechanics, because the story that I told applies also to quantum mechanics, provided that you buy into an ontology of particles. And then we can briefly come back to the question, why should you buy into an ontology of particles for quantum mechanics? But first, let's make clear that you can do so. So the quantum theory developed, going back to the Breuil and then Bohm, and notably set out by John Bell, is a theory that says that the ontology, the primitive ontology of quantum mechanics, also quantum mechanics is particles. These particles are permanent. they always have a definite position in space, and you can do this in a relational way. This has also been proven by now, that you don't need absolute space, but they are localized in space, they are individuals, they have a velocity, so then they have a trajectory, and then you have a law for the motion of these particles, which is called the guiding equation, where you put on the left side in the particle positions, and then you take the temporal derivative. And on the right side, there's a mathematical apparatus that gives you an output how these particles move. This gives you, if you put their positions in at the time, the output is the temporal development of the position. So the velocity by means of the quantum mechanical wave function, and that wave function develops according to the Schrödinger equation. And you need here, the big Q is the whole particle configuration. At the end of the day, the whole particle configuration of the universe. And that's how the Bohmian theory implements quantum entanglement and the quantum non-locality proved by Bell's theorem and the subsequent experiments. So it reproduces exactly the statistical predictions of quantum mechanics on the basis of a particle ontology, provided that the law is such that it connects the development of the particle positions in a non-local way. And then you can prove in this theory that if you ignore the initial particle configuration, so if you don't know where you bring in the usual tools of Boltzmannian statistical mechanics, you ignore the initial particle configuration, you take an equilibrium state as the initial state, the typical evolution, etc. And then you get Born's rule and quantum statistics out of that. So this is a determinist theory, and by the usual way, as you get from classical mechanics. I mean, it's not classical here, but the procedure is the same, how to get from a theory with a deterministic law to probabilities. So nothing new under the sun here. So that the freaks who think that quantum mechanics changes everything, that's bad news for them, but it's good news for other more simple-minded people who want to know what quantum mechanics changes exactly. It changes the dynamical structure, it changes the law. You need a law of something like this here, which applies in the first place only to the universal particle configuration and the wave function, instead of some other law. You won't get along here with an Einsteinian local field law, and you would not get along either with a Newtonian force law. So that changes, but the rest can be the same. And you can do the same with quantum field theory. And as I see the time moves on, I leave this for the discussion if someone is interested, because the more complicated the physics gets, the more complicated, I mean, the philosophical account gets. But the gist is that you can do it. You can do it with permanent particles and the law of motion for these particles. And since we don't worry about the dynamical variables being literal things that sit in the particles. In this case, you would need negative energy values to do it for quantum field theory, but that's not a problem, since energy is not some sort of substance out there in the world. And what is important now is to see that you can treat the wave function in a Humean manner. That's what is called Bohr-Unionism, also Bohmian Unionism. It is a dynamical parameter and the law for the overall particle, for the evolution of the overall particle configuration, as we did with masses and charges for classical mechanics. And it is literally speaking located in the overall particle motion. So it's nothing over and above in the ontology. So when you read physicists, there's a lot of confusion about what, sorry, this is I should not speak in a pejorative way. I say the physicists tend to take the wave function literally the existing in the world, but it can't be a field in physical space. Then you get a lot of confusion. Clear all of this confusion up by saying the wave function is therefore its dynamical role for the particle evolution and located in that. evolution. And this solves the quantum measurement problem, and that would be the argument for that. And why it is the best solution to the quantum measurement problem is also something for the discussion, or for the coffee, or for another occasion. So to sum up, the argument is that we need these dynamical variables. They are defined in terms of what they do for the particle motion. Putting them into the ontology does not give you any deeper gain and explanation. Think of Molière on dormitive virtues. So why do people fall asleep after having consumed opium? Because opium has a dormitive virtue. What is the dormitive virtue? It's what makes people fall asleep. Why do particles have mass? What is mass? Mass is what makes them move in a certain way. Why do they move in a certain way? Because they have mass. It gets circular and gets only into trouble. So if you think of these as intrinsic properties, how do they reach out to other particles, etc. If you go to quantum mechanics, you have these books that fill a library, how a wave function or entanglement relations or structures can be out there in the world and make particles move, and you bind them together. Well, particles just move. They just move, and so in the sense they change their spatial relations, and all the rest comes in through that motion and is located in that motion, and thereby enables us to make a good theory of that motion. So what I take to be the permanent question when it comes to philosophy or ontology of physics is to ask, what is the primitive ontology? What is there primitively out in the world, according to what you take the best guess as to that? And what then is the dynamical structure? So what then, so these are the three questions from the beginning put into the terms that I would like to use to get a simple and nevertheless empirically adequate answer. So what is the primitive ontology? What is out there simply in the world? How does this behave? So what is the dynamical structure you have to impose in order to get an account of the change out of this? How does this explain the evidence? And as a simple-minded and in that respect conservative person, I think that we don't have to go beyond atomism, but just do a philosophical analysis of what it comes down to, namely to point particles individuated through spatial relations, the change of these relations, and on that basis you can account for everything else. And the nice thing is that this is a robust scientific realism that does not fall victim to the standard objections from the pessimistic meta-induction and underdetermination, because the primitive ontology remains the same throughout all these changes, and what changes and about which one can make pessimistic inductions from ones, and what one may take to be underdetermined is the dynamical structure, because that changes as we make progress in representing the actual particle motion. So I think I have given a sketch of what I take to be the answer to this question that will be such that you may have a lot of questions, objections, or simply expressions of disbelief or whatever it may be now. So thank you very much for your patience up to now. And I think I will try to stop sharing the screen now so that we can see each other.
Well, thank you very much for your talk. We will have now time for questions. Please raise your hand by using the functions that on the so that I can see on the right-hand side of my screen. So, well, who wants to ask questions of clarification or doubts or? Okay, nobody wants to start. So I will. So, well, thank you very much. I'm very much convinced by the fact that, I mean, you raised in a very concise way the most important questions, the central questions for any philosopher of physics, and I agree with many things that that you suggested. I also think, however, that there are some difficulties nowadays, especially with respect to quantum theory of gravity. So my question is, have you thought about the, so to speak, the application of what you suggest in terms of ontological commitments to, have you tried to apply your view to quantum gravity models? Let's call them models, because
yeah, I mean,
like a theory.
Sylvia, you make life more complicated for philosophers as it is, okay? So quantum gravity is non-existing physics because we don't have any theory there that in any way makes predictions that could be tested. And that's what usually distinguishes physics from mathematics or logic or speculation. So they may do so, there are several attempts, etc. And I think we can go over the books and look into these attempts once we have a physical theory. So from my mind, this is, for the time being, these are mathematical structures, and you try to find out a mathematical structure that brings together the structure of general relativistic space-time, which is a curved space-time without a background, and quantum mechanics, which uses a background, the space and the background time, at least in the Schrödinger equation. And if you do it with the Wheeler-de Witt equation and quantum gravity, you lose time, and the problem is how this applies then to the world. Of course, a timeless equation can in principle nevertheless capture change, but it's difficult as long as we don't have a working theory. It's difficult to dissect what is the ontology of the theory, what is the dynamical structure. The relationalists, Julian Barber, are also engaged in coming up with a Leibnizian relationalist theory of quantum gravity. If that worked, I mean, that would be good. There are these guys like Carlo Rovelli who have their loop quantum gravity, but they are not clear on the ontology. And we know from all these quantum theories that they're trying to take or interpret their mathematical apparatus literally gets you into trouble. And of course, this trouble, I mean, if I can say a word about quantum field theory, which is existing physics, I'm happy and I'm cautious. I don't think that philosophers should take lessons from mathematical structure or draw ontological lessons. They may look into this, that's interesting, from mathematical structures whose empirical application or with empirical success or adequacy is an open matter for this time being. So I would warn to be cautious about it. It's an exciting business, but it's non-existing physics.
Well, I actually asked this question precisely because you mentioned the fact that we don't have to take the mathematics, well, the formalism, to tell us something with regard to the ontology, because, you know, I guess, I mean, you wanted to say basically that when dealing with mathematical objects, we are not dealing, I mean, we are dealing with a representation and with an interpretation, you know, of the physics. So yeah, I see the point, but I raised this question with regard to quantum gravity because there we construct through mathematics. So basically, we are investigating through mathematics a possibility, let's say. So something that, as you said, we lack of evidence, of empirical evidence. We cannot test this hypothesis, basically. That's the problem. So, but then I would like to know, and this is my last point, then I will leave it to the other people. My point is, I'm not a Platonist, you know, with regard to mathematical objects, but one could say, well, but we have good reasons to believe that mathematical objects do possess a degree of reality, even if they do not exhaust, so to speak, the physical reality. So we could say that a mathematical Platonist could even draw a distinction between reality and existence, and saying, well, but mathematics describes what is possibly real rather than something existing. What would your response be to this statement? Because in that case, of course, then a take on quantum gravity could be different from yours. But I would like to know whether you have some arguments against this type of position.
I'm cautious. Now you see, suppose I had this illustration there with a universe of 6 particles. And that's quite a small universe with a finite number of objects, 6 particles, okay? Now, when I want to represent their distance relations, I need real numbers, which are infinite, right? But my universe still is finite. There's nothing infinite. So I'm not a realist about mathematical structures, or maybe they may exist, but then I mean, then they don't belong to the ontology of physics. And it's a slippery slope. So you could say, of course, you need, I mean, Hardy Field had this strong nominalist project of science without numbers, but that's quite, I mean, there's some merits to it, but it's quite difficult. At least it's difficult to imagine doing science in that way. But when you say, well, some mathematical structures have some reality or so, then yeah, maybe, but then in a Platonic heaven, of which I don't think now, and you should not, you should sharply distinguish between both of them, because then you get on a slippery slope. So I think there could be a finite universe with n particles, and in this illustration n was 6, but in the real universe n will be a much more higher number, but it could still be finite. But of course, the mathematics I have to use will bring in infinity. So does this now speak against my universe being finite? I would say no. Or the universe may be infinite, but not for the fact that we have to use mathematics to describe it. So that's why, and so if I see only the mathematical structures as it's nowadays and quantum gravity, I don't see the ontology, and I'm skeptical, because when you look at the history of quantum mechanics, all sorts of claims had been made based on the mathematical structures, and all sorts of things had been thought to be ruled out. So particles had been thought to be ruled out. Normal laws, as we know them, had been thought to be ruled out, and all sorts of things. And then you run into these problems like measurement problem, etc. And you don't, then your theory loses touch with reality. And that's what we have in quantum gravity as it stands now. We don't have the touch with reality. We just have the mathematics. And we know from history that this is a dangerous road to go down for ontology. And it's in particular in the quantum case, because it led to all sorts of paradoxes.
Thank you very much. Are there other questions or remarks or doubts?
Now, if you're historians, or some people are historians in here, I say, so I tell you, you don't have to care about these determination problems and these chains and science. You can be a real scientific realist once the physics is done. So quantum gravity, I would agree that there's caution, but otherwise there's no reason not to be a realist, because realism can be a meager diet that does not commit you to all sorts of things you would be worried about being committed to. But apart from that, you can be really a scientific realist. Once you figure out the primitive ontology, science really tells you what there is out there in the world. But if this is fine with you, the better.
Yeah, maybe I have a...
Yeah.
Can you hear me? Yeah. No,
Yes,
a question. Yeah, I'm an historian, so
yeah.
I'm not the, let's say, a particularly expert of ontology stuff. So my question is very maybe stupid, maybe, I don't know, strange. Can you make a difference? So if I clearly understand what you're saying, you're making a difference between an ontology of the natural worlds and an ontology of a theory, so an ontology of physics. Or so when you talk about ontology of physics, it's not clear to me if you are in the theory or in the natural world. I don't know.
I'm in the world, always in the world, because the theory is about the world.
Yeah.
But the problem is that the theory uses an apparatus,
yeah.
which does not go into the ontology. So you have to purge the theory to look what really is in the ontology.
Okay.
Because otherwise you get into the troubles I just replied to about the Sylvia. So think about in the Schrödinger equation, for instance, you have the imaginary number, the root of -1. Now, two, there may be out there in the world, so you may have 2 apples or 2 trees, but you cannot have imaginary numbers that cannot correspond to anything in the world, but they do a job in the theory. So that would be an extreme example where you would say, okay, that's something that does a job in the theory, but it definitely does not belong to ontology. And then I would put on the theory side a lot of things, even wave function, masses, etc. And say, okay, of course, the propositions using them are true. They are somehow located in the world, but they are not per se things or entities that belong to the ontology. And I think that's the proper job of the philosopher. The physicist just uses their theories, and they are happy if they get predictions, and then they can make calculations and do experiments, etc. But the philosopher has to figure out what does the theory really tell about the world. Mm-hmm. And then it's ontology. And of course, you do it on the basis of a theory, because, I mean, unless you have God's insight or so, you cannot but rely on scientists that they do good theories about the world. At least it's better than common sense or so. And then you have to find out what is it in the theory that the theory needs really to postulate about what there is out there in the world to work, and what is its conceptual apparatus to represent what there is in the world and its behavior.
Thank you.
I would like to ask a question,
yeah,
or maybe it's a comment, I would say.
Yeah.
So in your slides, you mentioned that mathematics is merely a representation, but it doesn't really go into the ontology. I want to ask, how much do you think the ontology that you presented itself is mathematically based? For instance, you're talking about individuation of particles. So there's a notion of, we can count them. But doesn't this assume locality first? I mean, you need to have
what? Sorry, I did not.
Local structure, a locality.
Yes, yes.
You need to assume that in order to be able to localize every node, let's say. Even though there is no metric you mentioned, but I feel that there is some, there's a standard topology employed in your ontology. So I would be curious to think what you would say if somebody suggests that actually there is a bit of mathematical bias goes into the ontology that you present.
Yes, yes. Thank you. You caught me there. Yes, it's true. Yeah. And the bias is that we're talking about nature. So you could, for instance, suppose Descartes is right. Then there are two things follow. Descartes says about the natural world, it's extension. Okay, and by thinking of the natural world in terms of extension, you somehow bring in some mathematical structure in your ontology. And this is something, some geometry goes in there, and I mean, at least some topology goes in there. It must be such that you can build a metric on it. So the triangle inequality goes in there when you talk about distance relations, etc. So of course, some mathematics goes in there, but not, for instance, infinite numbers. So you're right. And now Descartes thinks that there are also souls and or minds, res cogitans, and then you would, then if this were so, then you could also think about there are many minds out there, and what individuates the minds, and would that be something non-mathematical to have a contrast? But at least for nature and extension, you need something mathematical, and that's a subtle discussion. So I could, I mean, if you press me further, I would probably have to concede that also angles go in there, so that you can come to these knots and graphs that I draw. And of course, there goes in something, but I would say there don't go numbers or any such thing, and that are no abstract objects, but something that defines your extension and that enables you to take distance relations to individuate objects. So in the notion of distance, and in the idea that distances exist out there in the world, something of mathematical structure goes in. And still, I would, of course, defend that the topology and the metric, etc., is our means of representation, but it refers to something that is out there in the world, and that something somehow is somehow affined to mathematics in a way that if you think there could also be other things out there in the world, so suppose Cartesian souls or angels or what have you, that would not be subject to mathematics in that same way. I don't know about Cartesian souls, but suppose they exist, etc., then somehow they would have to be contrasted from the physics. So if you think there's the ontology of physics, but there may be more in the ontology, and then you would say, of course, the ontology of physics is distinguished in a way that it requires and enables mathematical representation, and that means there's something that is affine to that representation out there in the ontology, which is not so in other domains, if there are further domains of ontology. Yes, I have to concede that point. Although, of course, I cannot separate it from the language, so I always have to use the language.
Yeah. Thank you.
Thank you. That was good. It gives some points back to Sylvia that I cannot, I mean, I can wait, I can evade some things, and I can evade, I hope, to derive my ontology from mathematical structure, but that the world somehow is so weak. Wigner was that guy, and he wondered why it can be that our mathematics are so successful. Yes, of course, because the world is extended and characterized by distances and motion, which enables mathematical representation. And if the world were other, so if we had only Cartesian souls or whatever in the world, then that would not be so, yes.
So are there other questions? Luciano, do you want to ask something? Or Oliver, please go ahead.
Yes, I provoked the historians, so.
Successfully so, yes. No, I'm afraid I will have to ask a contextual question because, as you know, I'm a historian of science, and I can't really ask anything intelligent about your talk, which I liked very much. But I'm interested in how well, scientists interact with each other, and I know that you have been working with physicists and chemists for 25 years or longer. And I always found that admirable. that you searched and successfully searched for contact with them. You were working together with them, research projects, summer schools, and all the rest of it. So I think my question is justified because this is also a bit about interdisciplinarity, you know, and how it may work or not. And what is your decade-long experience with that? What do physicists say? How do they react when you present them with that kind of minimal realism and that primitive ontology? Does that make sense to them? Is it even interesting to them? And do they even learn something in the sense that it's kind of fruitful in both directions? Obviously, you've learned something from physicists. According to your perception, is it also the other way around, or is there fruitful dialogue going on? That would be my question.
Well, obviously, I learned a lot from physicists to the extent that I'm able to learn physics, etc. Because all these, when it comes to quantum mechanics, quantum field theory, and things, you need an expert, because otherwise this may come out nonsense. I mean, Newtonian mechanics, the three laws are easy, and this may go there, but it's like in all businesses there, I mean, the physicists are not one community in the sense that they all have the same interest like the philosophers. So a philosopher of science always is a bit between philosophy in the sense of an a priori analytic business. So think of analytic metaphysics or analytic ontology. So when I did my habilitation at Konstanz, there were many great philosophers, and one of them was Wolfgang Spohn. And Wolfgang always said, okay, yeah, he read the things about the metaphysics, but he thinks that philosophy is about metaphysics and logic and possible world, and the real world is messy anyway, and that's not of interest for him. And so you have this side, so they would do great metaphysics, but these philosophers would not be interested in real science. And in the scientists, you have those who are just interested in making their theories work and the experiments done, but don't care about ontology. So if you give such a talk as I gave first to you, to physicists, you would have a lot of them say that does not tell them anything because they don't care about ontology. They just take their theories at face value, and they're happy if they can derive predictions and if the laboratory works, etc. And those would then not be the physicists who are interested in philosophy, or once they are forced out of their laboratory by retirement, then they get interested or so, but they may also get interested in religion and things like that, but that's then not, I mean, the real interdisciplinary work. So you need some philosophers who are interested in science, and some physicists or scientists who are interested in ontology, I would say. And they are there, and I mean, the obstacle or the problem is that when, I mean, in particular in the European continent, we all know this, if you want to get a job in the university, and if you're not so happy as Oliver, you are to get a fellowship just for research, a permanent position as a researcher, then they say, well, we have a department here, we have a curriculum, and we have to teach this and this and that. So we need a philosopher, and it's a hobby if they do also philosophy or physics or so, but for our teaching, we don't need this. And if you're a physicist, they would say, okay, we want your physical results, we want your theorems proven. If you're a theoretical physicist, you want you do the experiments, and if you care about ontology or philosophy, you may do so in the evening. So I think the structure that we have in the universities, the separation, so philosophy usually is in humanities, physics is in science, and we don't have really an established way of work on foundations. So logic belongs to foundations, mathematics, physics in the sense of caring about what was called natural philosophy in the happy or less happy times, I don't know. You investigate in history of science, etc. This has gone lost for institutional reasons. So that makes this institutionally difficult. because to get your job, you have to do disciplinary work. And is it interdisciplinary? But that applies probably across the board to all these areas. For interdisciplinary work, you get nice words on a Sunday, but in particular, if you put PhD students on that, the question always is, what shall they do afterwards? You have to go into one of these disciplines and play the game. Otherwise, you are out of the game. So the answer is twofold. First of all, of course, it's not an issue about communities, because it's an issue about what interests people have, and some physicists are interested, some are not, and that's completely legitimate. The same for philosophy. But so that's all fine. Some philosophers do more a priori things. Other philosophers do more things turned to empirical science. But there's an institutional problem we all know of. And I don't know how to address, what's the best way to address the institutional problem, because we cannot change the structures of universities, disciplinary curricula, etc. So, but I think in some way it has become better, because it has become more open-minded. In other ways, it is not so good. But yeah, so I think if there's something to be addressed, then one should think about how one can address the institutional problem. And when you do such research projects, as I did also, and when you want to have funding for that, it's an issue of luck. You might find referees who think that's interesting, and then you find referees that says, but that's of no importance for physics or no relevance, etc. And that is how it goes. Yeah.
Thank you.
Thank you.
Thank you very much. Are there other questions?
We'll try to sketch a question. Let me try. Because I not feel extremely comfortable when talking about ontology. I'm a physicist.
Yeah, what are you talking about? You talk about the world, don't you?
Yeah.
Sorry, go ahead with your question, but you should feel comfortable.
So, because when we talk about distant relations or things like atomism, in my mind, it's very difficult to not have a direct relation with the absolutes. For instance, if you are supposing the structures of the points and talking about, I don't know, point A, point B are nearer and the other is further.
Yeah.
There's always some sense of background structure in a distant way, because if something is nearer, one can move it or sketch that there's this underlying space in the ontology we are talking about.
No, I mean, I would say no, because this is clear that when you use the language, etc., it's much easier to have an underlying geometry and use absolute notions. But then I think, I don't know whether you know Julian Barber and his collaborator from Oxford, they developed a relational theory. They showed how this can go, but the theory gets more complicated and the language gets more complicated if you do everything in relational vocabulary, but you can. I mean, they have proven this, and the discussion can then be that they will need something more than I gave you here, but it's all relationalist, so it's only about ratios of distances. But they may need angles, etc., but they don't need an underlying space. So you can do, and you can do physics on that basis, but you would not be interested in it as a physicist, but you would be interested in it for ontology, because you want the things that are invariant for your ontology. So when you think whether there's an absolute space out there in the world, you know this Leibniz-Newton exchange of letters. So Leibniz always makes points when he presses Newton on what can that absolute space be, okay, that underlying space. If you think it's simply out of there, if you think of it in ontological terms, it makes no sense. But of course, it makes a lot of sense if you think about it in terms of how to do your physics in a concrete manner. And there, of course, Newton gets the upper hand about on Leibniz, and it took several hundred years for people. Ernst Mach was involved in that, and then Barbour to work out really a relational theory. But you can do it without underlying space, but it's counterintuitive. So perhaps Kant is right in the sense that he says that space and time are some forms of intuition, so we cannot imagine a physical world just with relations without embedded in an underlying space, etc. But yeah, even if this is so, there still remain the arguments that when it comes to ontology, it's not so good. So the questions about ontology, I fully agree, they are different questions. I think they should be of interest to you as a physicist because you want to work out what there is in the real world and how the real world goes. But when you do physics, I mean, when you do a concrete physical theory, ontology makes your life more difficult, and your life is already difficult enough.
Great. And I have another question. I don't know if you know, there's a proposal, sorry, I will go back to quantum gravity. Mm-hmm. There's a proposal by, I don't remember if it's Haggett or Woodridge or maybe both.
Yes.
In which you have your underlying theory and your underlying quanta, which are interacting in one can say adjacency structure, like not one next to the other.
Yes.
But then they argue that at the effective level, when one reaches general relativity, probably things that are closer in the fundamental structure are not anymore in this like nearer structure at the general relativity level.
Yes.
And this is because technically speaking, the general relativity, it's quantum superposition. So I don't know if you agree, or how this kind of non-locality accommodates when one talks about distance relations, because there seems like a multi-level degree of
yes.
reality. One,
yes, I agree that
underlying things, there are things that have a distance interpretation, and then in the other level, there's another distance interpretation. So how do we make a bridge between both distances, as they are not the same ontology for calling distance?
Yes, thank you. So I agree, of course, that general relativity should come out as something from an underlying more fundamental structure. Okay, that's clear. But then the issue is, so Chris Woodridge and Nick Hackett claim that in the fundamental structure, they don't have anything that looks like Cartesian space. So they don't have anything like distances as I propose them, which is quite conservative. So they think it's completely revolutionary. And then my problem is, and we've not settled this as of now, so my objection stands that I say they switch to purely logical structures then, okay? So I tease Chris Woodridge, who's in Geneva, which is right at the other end of the Lake Geneva, where Lausanne is, and it's called Lake Geneva because Geneva is the more important town, but Lausanne is the other end. So we are near and we are not near, so to speak. And Chris is so think of God and angels. So God has his angel, has and how does he order? How does he make an order in heaven? It won't be anything that approximates a space-time of general relativity, I guess. So the problem is that your underlying structure may lose too much, so that you go. So Chris is a fan of causal set theory, so you would write this down in axioms of causal sets, etc. And then the issue is how on earth, but that was what I also replied to Sylvia, how on earth are you going ever to get empirical results out of that? If you smuggle in something like a relativistic space-time and apply it to that and presuppose from the outset that you have the metric of general relativity somehow there, that it may be a useful logical analysis, but you would have to deduce it. So for general relativity, I would think this relationalist program of Barber, but it's I mean, insofar as it's worked out, that it's classical, they can show you how they get the something equivalent to the absolute spatial-temporal matrix of Einsteinian curved space-time from a purely meager relationalist structure. But this relational structure still has distances in it. And so the quantum gravity issue, Hackett and Wüthrich think that the underlying thing is nothing like the distances with which we are familiar. And then it gets difficult to see how they could get to empirical results. And of course, they would say that they did more to the job, but they would agree that they have not done completely their job. And then the question is more or less about where you, on which horse you put. Do you think that this can be done on a basis as they propose to really get to general relativity, or this cannot be done? And I'm rather skeptical, but of course they shall go on with their work and we'll learn something from it. And I may have to go over the books at the end of the day, but the end of the day is once you have empirical predictions, once you have really reached the physics. Yeah.
Thank you. Are there follow-up? No? Okay, so, well, I would like to thank you very much again, Professor Esfeld, for having opened the season of our seminar series. And I also would like to thank everyone for being here today. And we shall reconvene all together for the next meeting on the 20th of October. Thank you very much again.
Yeah, thank you for all your contributions there. Yeah.
Thank you.
Keep in touch. Yeah.
Yes, let's keep in touch.